Hello, today we're going to take a look at the paper, A Review of Seabird Energetics Using the Doubly Labeled Water Method. This paper was published by Scott A. Shaver in 2010. The doubly labeled water method is a great tool for scientists to use when we're looking at free-range animals. It gives us a study of animals not in a laboratory setting, but more in their natural habitat. The first time this method was used, it was on a study looking at penguins in the early 1980s. Since that, there have been hundreds of species and hundreds of studies using this method. And of those studies, about 50 species of seabirds have also been studied using this method. The different seabirds that have been studied have been examples from every major taxonomic order, which gives us a really good idea of how these animals survive and some of their unique metabolic traits. Although the basic methodology of this method has remained the same since those early studies in the 1980s, there have been several different equations that are used to calculate the field metabolic rate of animals, which is something that is derived from the final isotope levels collected from the species in the studies. These 9 different equations have come about from many different ways. Some are improvements on old equations, and this paper will take a look at these different equations and compare them and show how there might be some discrepancies in using these different equations depending on the situation and the study they're being used in. In fact, this paper shows that in some cases there can be a variation of 45% in that field metabolic rate, which in turn is used to calculate the carbon dioxide output of the animals. The second half of this paper looks at how using the doubly labeled water method along with new biologging technologies can give scientists some more clarity when it comes to their studies involving metabolic rates of the species that they're looking at. Biologging technology is basically a broad term for many different kinds of technologies such as tracking devices or different types of electronic logging technologies. These technologies can give scientists a closer look into what these animals are actually doing while they are being part of doubly labeled water studies. The author of this paper looks at albatrosses as his examples to prove his points for both the use of the different equations and for showing how using biologging technologies with doubly labeled water can give scientists a clearer picture of the subjects they are studying. Understanding how animals use energy that they put into their bodies and how they spend it is essential in understanding their physiology, and from this information, scientists are able to learn a lot about animals' ecology, and this information is very important to the scientific community. That's why there has been so much effort put into energetics and understanding how energy is used by animals, and there's also been a lot of effort put into studying the best way to measure these animals' metabolisms. This metabolic research has been conducted in both laboratory settings and field settings, but when it comes to field settings, the doubly labeled water method is the standard method in measuring animal metabolism. To better understand this review, you need to understand how the doubly labeled water method works. This was covered earlier in the class, but as a brief review, in the doubly labeled water method, an animal is collected and they are injected with what's called an isotope of oxygen and hydrogen, which is then absorbed and metabolized by the body. The animal is then re-released into their natural habitat and allowed to go about their normal behaviors, which in turn expends the normal amount of energy the animal would expend in the wild. After a set amount of time, the animal is recaptured and a second blood sample is taken. From this sample, the scientists are able to look at the measure of isotopes compared to the sample taken at the initial capture. From these isotope levels, scientists are able to calculate carbon dioxide levels. This carbon dioxide calculation is the one that this paper is taking a deeper look at. There are several different equations, and the equation used might have an outcome on the final results of the study. As I mentioned before, since its introduction in the early 1980s, this method has been used on over 230 species of animals, and of those, 50 of them have been seabirds. Seabirds make excellent test subjects because they have many unique traits when it comes to their metabolism. They don't produce many young, and they don't produce many young in a given year. They're also delayed in maturity, so it takes them longer to reach adulthood, and their lifespans can be quite long. In fact, these unique traits are even unique and specific to seabirds when comparing them to other terrestrial birds. Many seabird species are threatened, and there are many conservation efforts in effect to help protect these seabirds. So any understanding that scientists can have of these animals further than what we do now can be crucial in protecting them in the future. So now we are going to look at the topics this paper is going to review. This paper is going to review several of the equations used to calculate carbon dioxide before those numbers are used to calculate the field metabolic rate. They don't examine all 9 in depth simply because some of the equations they are looking at are actually revisions of older equations that count as part of those 9. And then the paper is going to go on to look at how we can use doubly labeled water with data loggers to make a more refined energy budget for animals. Now, an energy budget is basically a scientist's way of looking at the amount of energy coming into an animal through food, and then the amount of energy that an animal expends on their day-to-day activities. So by understanding this, scientists are better able to understand what a species needs to survive on a day-to-day basis. So as I mentioned before, there are 9 equations that are used to calculate the carbon dioxide of that final blood sample taken from the recaptured animal. Now there are 2 main distinctions between all of these equations. First one being whether it's a single or 2-pool model, and then whether or not that equation corrects for that isotopic turnover. So the 4 equations that this paper is going to take an in-depth look at are basically the original equation used in the earliest studies, the most widely used equation, a single pool equation, and then a 2-pool equation. And as I stated before, the remaining 5 have either been updated or replaced by one of those initial 4 I just mentioned, or these equations are more commonly used in human studies. The doubly labeled water method is used in a lot of human studies, but this paper would like to focus more on non-human animal studies. So to compare these 4 different equations, 5 different albatross species were studied for 2 to 11 days, and a final blood sample was collected. These 4 equations were then applied using the same raw data from the end result of that blood sample, and then the results of the different equations were compared. 5 species, it was seen that the most widely used equation produced the highest carbon dioxide estimates, while the two-pool method produced the lowest. Now, it is kind of a rule of thumb when conducting a doubly labeled water experiment that your choice of equation is somewhat dependent on body size. A lot of times people go off the rule of thumb that single pool equations are best for birds when they're 4 kilograms or less, but then there are others that say that this hard 4-kilogram rule might not be quite so clear cut. This is definitely something that may require further study for a clearer understanding. And when looking at single pool equations, there's even variation within the set of single pool equations being used. So that is also something that might need to be looked at further. The author really concludes in the end that it would be probably in everyone's best interest to provide as much raw data as possible when conducting doubly labeled water studies. That way, if other scientists want to go back and use a calculation that they might feel is better for the study, they will have that information available to them. It is common knowledge that the amount of energy going into the system must be balanced by the amount of energy going out of a system. So basically, animals need to take in as much food to produce the amount of energy needed as they are spending on their day-to-day lives. This assumption allows scientists to create an idea of what an animal's metabolism measurements may be. Understanding an animal's amount of energy expenditure can be a big help when trying to understand the broader picture of how that animal survives in its environment, and that in turn can greatly help with conservation efforts for these animals. One way scientists can show this data is through a time-energy budget. Basically, over time, how much energy is expended by an animal. So that way we know how much energy needs to be taken in by that animal to survive. The more information scientists have when creating these time-energy budgets, the more accurate these budgets can be. Now, by combining doubly labeled water studies with microprocessor technologies, we are able to look at animal behavior, their distribution patterns, their activity, and many other things going on within the animal and around its environment while we are studying its metabolism using doubly labeled water. Pairing biologging technologies with doubly labeled water really goes back as far as doubly labeled water studies have. In the 1980s, scientists tracked African penguins' swim speed to understand the energy expenditures used when penguins were swimming and foraging. And as you would expect, and as was proven by the author in this paper, the more energy that it is expended, the more activity the animal is doing. Relating once again to the albatrosses, the author looked at many doubly labeled water studies and was able to show that albatross have the lowest field metabolic rate when it's equivalent to their body mass. This is because albatrosses have an excellent soaring ability. Flight doesn't cost as much energy for them as other birds who use the time more actively flying. There are a few other things to consider when looking at doubly labeled water studies. First being that there are some differences in results of doubly labeled water studies compared to open flow respiratory measurements, which is another way scientists are able to study animals' metabolism. It's also been shown that doubly labeled water might not be accurate or efficient when we're looking at animals in marine and aquatic ecosystems. This was shown when looking at sea turtles, since they have a high water flux into and out of their body with a very low metabolic rate. So this might throw off some data. These effects don't have any influence on seabird studies, but it should be a consideration if you are looking at a doubly labeled water study that focuses on any aquatic or marine animals. So in conclusion, it has been proven that doubly labeled water is a very effective and essential research tool for scientists, and this has been proven over and over again with over 300 published studies using this method. And as effective as this technique is alone, it can be even more effective when we're pairing it with different biologging techniques. There are many new threats to species all over the world as our climate continues to change and habitats begin to diminish for these animals. So using doubly labeled water might become an essential tool in monitoring species and their changes from year to year. And while this is a very effective technique, there is always room for improvement, and research should continue to be conducted on this methodology to further refine equations and eliminate as much error in the study method as possible.